Welcome to the course Simulation Techniques in Modern Wireless for Emasters course. In today's lecture, we will give an introduction to the course and we will look at the grading policy and the tentative course content. My name is Dr. Abhishek Gupta. I am a faculty in Department of Electrical Engineering at IIT Kanpur and I will be your instructor for this course. In this course, let us look at first what is simulation. So, to understand the dynamics of a real world system or a function of a physical system, we need to model it and imitate the step by step operation of the system using a computation tool. So, the other alternative is of course to do an experimentation on the real world system, which may be sometime not feasible or sometime it may be a expensive technique. So, to reduce some cost and for convenience, we can just simulate the system in the using a computational tool using computers. So, if I want to define simulation, I can just say it is a step by step imitation of a real world process. And these systems can include any physical phenomena, for example, Brownian motion or path of a projectile, or even man-made devices such as robots or motors. And this computational tool we are talking about can be either a hardware based tool or a software based tool. So, you can simulate the system using computer and then you will be basically using a software, or sometime there are hardware based simulation tools which will try to mimic the real world systems. For example, a FPGA based system or the human in loop simulators. So, let us look at an example of a system. Suppose we have an object under external force F, and if the location of the object is x, then the force applied is minus kx. So, it is in the opposite direction of the location. And I am looking at the distance from a reference point, we can call it a origin. So, suppose the initial location is 10 meters and the object is initially at rest. So, the velocity is 0, and if you leave this system, then due to the force the system will start moving. Suppose the k is given as 1 and the mass is given as also 1 in standard units, then our goal is to understand what will be the location of the object with respect to time t. So, this is actual physical system which there is some force or there may be many forces on this, and we want to understand how this object will move with time. So, what we need first is to understand the dynamics of the system, how does system behave. So, this is a simple system. Here you can denote the location of the object by x t and the velocity by v t. So, both are a function of time. And now, if you look at the acceleration of the object at time t, that is given by force divided by the mass, and the force itself is a function of time, because force is equal to minus kx and x is a function of time. So, I denote it by x x parenthesis t. So, the force will be equal to minus kx parenthesis t, and if I divide by m, the acceleration will be equal to minus k by m x t. So, if this is the acceleration and we focus only on a small time duration, then we can assume the acceleration is uniform in the small time. So, acceleration is also changing with time, but if we look for a very small time interval, then we can think that the acceleration looks uniform or constant, and then the change in the velocity will be given by acceleration multiplied by the time interval. So, acceleration is at. So, if I multiply by delta t, which is the time interval, I get the change in the velocity. So, if the initial velocity at time t is v t, then the change is a delta t. So, overall the velocity at time t plus delta t would be equal to v t plus a t into delta t. Similarly, you can apply the same formula to the position also. So, the rate of change of position is given by the velocity, and if we know the velocity, which is again a function of time, but we can think it is a constant, then we can multiply delta t to it, and that will give us change. So, change after the time t plus delta t is equal to x t, which is the initial location, plus v t into delta t. So, what we got here is, if I know the location and the velocity at time t, I can calculate the location and the velocity at next time, which is after delta t time. So, now what we can do is, we know how to do this operation in one time interval. So, if I want to simulate the system, if I want to look at the behavior of the system from time 0 to t, what we can do is we can divide that overall time duration to small intervals, each of size delta t, and then we can just repeat the process. So, we start with the initial location, which is at time 0 the x is 10 and the velocity is 0, and we change time t from 0 to 10 seconds with some small steps. For example, you can take 0.1 second or 0.01 second and like that, and for each interval you compute first the acceleration in that time interval given by minus k by m into x t, and then you update the position and the velocity for t plus delta t time by taking the previous velocity at time t and adding their rate of change multiplied by the time interval. So, the previous example which you saw can also be solved analytically to derive the expression of x t. This was a very simple system. You can write the differential equations and you can solve that, and you can actually get the x and v in terms of time t. And if you solve it, you will find that this is actually similar to simple harmonic motion, and the x t is nothing but a cos or sine function. But the system dynamics can actually be complicated. So, you may have forces which may depend on time, velocity and x in linear or nonlinear way. There may be random factors also. For example, there may be some random noise, or there may be more terms like there may be dampening and there may be other factors. And if you include all those factors, probably the analysis may be little bit difficult to do. So, of course, if you want to solve the system analytically, we need to assume some condition, or need to, for some specific cases we can solve it, but we cannot solve it for any possible configuration. But simulation, this is not the case with the simulation. Simulation provides an easy way to understand the system dynamics and computed performance, because you looked at the steps and we are just computing the acceleration regardless of whatever complicated way it depends on the system parameter. You can still compute it numerically, and you can put that value and compute for next time intervals. So, the complexity is not an issue with simulation. Of course, it may make simulation a little bit difficult. You may have to implement many steps, but there is not a bottleneck in this process where system becomes complicated. But analysis is, however, affected by the complication. If your system is complicated, probably you may not be able to get a closed form expression. So, that is the main benefit of simulation, that you can regardless of the complexity of system, it may be almost always possible to write a simulation and perform the task, if you just understand how the system behaves. So, system dynamics is the important part. If you know how to model a system, how to how these different parameters are changing with respect to input and how to compute the output, then you can perform the simulation. But there are of course some issues with the simulation. It's not like a golden thing which always work. So, one thing is computation tools, mainly software, support discrete evaluation. So, your system may be a continuous time system, which means it may be evolving continuously with time. But if you want to perform a simulation in computers, you have to convert the system to a discrete time process. So, you need to first discretize the system in time axis, which means that you need to sample the system. And similarly, the signal value is also stored, suppose in a double format, then double format is also has some limitation, right. It cannot probably store any possible value you want. So, if I look at the discrete in time axis, then you will sample the signals with time, and the question remains what should be that sampling time, right, how small you take this delta t, right. If you take delta t very large, then you cannot probably assume that the acceleration is constant in the previous example. And if you take delta t very small, then you may have to do many iterations. So, you have to choose a optimal delta t, so that you are able to capture the variation of the system correctly, and also you are not doing unnecessary computation. For example, if acceleration is almost constant in interval, there is no point of further dividing the interval into small parts, because the accuracy you are going to get is probably not worth the time the computer is spending. And then again you have to discretize in signal values also, because as I said, signal values are, suppose it is stored in a double format, then again there is a precision of double numbers. So, you have to quantize the system, and probably most cases software itself handles this when it represents a number by a double or any precision format. So, there is a concept called machine precision. So, every software tool has a precision inbuilt, which we sometimes denote as epsilon. So, you cannot represent two numbers which are just different by epsilon amount. The machine just thinks that both are same numbers. So, this is the smallest accuracy you can represent any number on the machine. And then we talk about that there may be random effects. So, when you have random effects, many times we are interested in average behavior. So, if you want to look at the average behavior, you have to simulate the system multiple times. Every time the system behaves little bit different because of the random factors, and then you take the average out. So, then the question comes, how many times you need to simulate the system, and again here the more number of samples you take, the better average you get. But again after some accuracy, if you are again doing more iteration, that may take your simulation time, which may also be precise, because computer has a limit. I mean, it takes some time to do each simulation. So, if you are doing, if you want to do 10 times more simulation, it will take just 10 times more time. So, let us see how we can simulate a communication system. So, let us talk about a typical communication link. Suppose you have a transmitter and a receiver, and there is a channel in between, and we want to simulate the system, whatever the physics behind it, and our goal may be to understand how the system performs. So, we need to first understand the physical process behind this communication link, right. So, I am not going to talk a lot about what is the actual physical process or how this communication system work, because there are other courses which deals with this in complete details. So, but I will assume that you know some basics of communication systems. For example, a typical communication link can be written in the cascade of these phases. So, you get some masses bits, then there is a modulation block which converts these bits to symbols, transmit symbols, and then you transmit these symbols to a physical signal, right. So, you may be converting the baseband to a passband signal, and then there is a channel which may take this signal and may attenuate it or distort the signals via random noise. So, what at the receiver you basically get a signal, physical signal yt, which is a distorted and attenuated version of the original transmitted signal. And then at the reception you convert probably to a baseband, again you get some receive symbols which you can demodulate and get estimate the bit which was transmitted. So, the design of this system is to be able to guess the transmit bit exactly. So, this b hat, which is my estimate of what was transmitted, should be equal to b in ideal cases. So, what is the physics behind it? We if you want to simulate it, we need to generate some bits, then we have to apply these steps like modulation, demodulation, and of course, we have to mimic the channel also So, channel may have some random factors. So, you have to mimic this random noises, and probably you have to artificially include noises. And the final goal is to evaluate the performance of the particular link. So, you look at what you have received and you look at what was transmitted, and you compare how many times you get an error, right. And you, if you, because of the random factor, this is again a random a result, because sometimes the bits may be correct, sometimes the bits may be wrong. So, you look at the average performance and you look at the bit error probability. So, you can evaluate the performance in terms of bit error rate, or you can also talk about signal to noise ratio, because this gives some idea about how much what will be the bit error rate. And then you can also talk about capacity and data throughput. So, there are different parameters, performance metrics, which you can look at depending on what is your final goal, what is the use of application of this communication link. And then of course, you may complicate this system further, because in modern wireless you use many techniques which need to be included in the system. So, the system will be expanded. So, you can include traffic patterns, right. Currently I am assuming the bits are coming continuously, but there may be some traffic pattern behind. Sometimes the bits comes in burst, sometimes they do not. So, when you factor in this one, you can talk about latency performance, that if I sent some packet, how much time it will take to receive that packet completely. And then sometimes there may be errors. So, normally we cannot ignore the errors, because the receiver may be interested in the complete data, and if the data is encrypted, even losing one bit, you just do not understand anything in the packet. So, you may have to acknowledge, and you have to again send repeat request if the transmission has failed. You can also talk about how to encode the system, how to do error corrections. So, these can, there are many simulation techniques depending on what generation of standard you are talking about, what application you are talking about. So, these can be incorporated in the communication link, and you can simulate even complicated communication links to finally get some performance metrics of the system. And then I have talked mainly from the perspective of physical layer, where you have you are talking about the bits and how they are converted to from baseband to passband, actually sent and then they are received. But there are other layers of communication also. For example, you have a scheduling layer, the medium access layer, you have the network layer, transport layer, application layers. So, those can also be simulated using similar process. So, in our course we are going to focus on physical layer only. So, now if you look at this from a system layer perspective, in past we just talked about a particular communication link, but a modern networks may have many such communication links coexisting together. So, in this figure you can look at that there is a transmitter and there are one receiver, and there are other transmitter receiver pairs also which are transmitting together. And if they are using the same frequency band, then they are basically going to interfere. So, if this particular transmitter receiver with this blue link is our desired one, the other links may be interfering to this one, and because of that you may have a cross link interference. So, instead of signal to noise ratio, you are going to talk about signal to interference plus noise ratio, and this interference will increase when you increase the number of links. So, with as this number of links increases, the analysis becomes more and more complicated, and it becomes really difficult. I do not think there are any closed form expression available for systems with multiple links. So, here you can only do simulations here. Of course, then you for particular specific configuration there are some results. For example, if you assume these links to be randomly located according to some Poisson point process or some other point process, then something can be done. But for a general layout, right, where this location can be deterministic, the analysis is really difficult because of many random factors playing a role here. So, let us look at the various aspects of a communication system. So, suppose you have a transmitter and receiver. So, if I look at from a network layer, there are packets which are being transmitted from this transmitter to the receiver. So, you may have a complete network and these are different nodes and they are connected by the links. So, if you want to send a packet, you need to find a sequence of hops which actually goes to the receiver and then you route the packet. But then again many packets are moving, so you have to schedule these packets also. So, here we talk about how these packets are flowing, how do we do routing, and then how do you give priority to different packets, how the switching is occurring. So, that we call network layer. Then we have physical layer, we are talking about the actual physical signal. So, we are not concerned with packets, we think from a bits perspective. You take the bits, convert to the transmit symbol and then actual physical signal in passband, and that is transmitted and there is a random factors which is finally received and you decode the bits. And how you make the packets out of these bits, that is the higher layer, that network layer perspective. But from physical layer we are mainly concerned with how to simulate these waveforms, how to simulate the physical effects of channel, how to do different baseband processing. So, that is the part of physical layer. And then you can look at this link and you will find that this is actually made from small blocks and each block itself is implemented in hardware. So, suppose if I look there are different blocks and if I suppose look at a particular block, there are various ways I can look analyze that block. One is of course, that block is implementing some algorithm. So, I can test that algorithm, how is it performing on a software like MATLAB. I can also think the block in terms of how the signals are being processed. So, you can actually think as a sampled version of a continuous time signals and see how you are performing sampling and how you are performing different filters on that. And then you can also think this from an actual hardware point of view, because eventually everything is implemented in circuits. So, how the circuits are behaving. So, you can simulate, you can make actual circuits, you can simulate the circuit using some kind of circuit simulators and look at how the behavior is. So, these are different aspects or different abstraction layers of the same system. And of course, what our goal is, that depends which way you want to look at. For example, if you want to simulate, look at how a particular device performs, right, then a filter performs, then you are going to do this hardware simulation. But if your system has many filters and many blocks in it, and if you try to simulate the whole system in from circuits perspective, it may take a huge amount of time, because you have to simulate a large system. So, in that case what we can do is we can simulate each block separately, see if they are working or not, and just abstract their performance and use that in the for a larger system. For example, if I know that a particular filter creates this output waveform given this input waveform, then I just use that relation to create the testing of the algorithms, right. I do not have to actually simulate the whole block again, because it may probably give the same result. So, let me talk about what is the focus in this course, because there are various aspects of communication system, various layers you can think of. So, in this course we are mainly going to focus on physical layer simulation, how we simulate the waveforms, how we simulate different blocks of the communication system, look at the receiver performance, and we look at the link layer also, where we talk about performance of a particular link, and we also talk about a system layer where there are many links and we see how we can modify our simulation to do perform a system level simulation. And then we will talk about various configuration of modern wireless systems. For example, you will see cellular networks, we will look millimeter wave networks, we will talk about ad hoc networks. So, we will look at different types of modern systems and see how we can simulate those systems. So, overall the method is going to be same, is just that there is some changes you need to do. we will take a hand-on approach, right? Instead of talking just theory, we will actually see how to implement that in a simulation software. And for that purpose, we will use MATLAB because it is a easier language. So, we will take MATLAB based example and see how these different things are actually implemented, and we will keep the theory minimal because the theory is again covered in a particular communication courses, and if I cover that again, probably we will diverge from our actual goal. So, we want to look at the goal is we would be able to simulate the systems. So, we want to look at the actual systems and how they are implemented. We will of course talk about some theory wherever that is necessary, and we will use some level of abstraction because you will see that when we go to system layer, there are many links and you cannot do a link layer simulation to all of these links. So, we need to model the links in a way that it does not complicate the overall simulation. And the same thing will happen on link layer also. Link layer is again made from many blocks. We cannot simulate the complete block with the very minute physical process imitation. So, we will model the system. So, that is also an important part of simulation. You need to understand how to model a particular block in a way that it does not overcomplicate the system and still you capture the overall behavior. And then whatever techniques we learn can be applied to other layers also, an abstraction layer also. So, this course will not limit your ability to only do physical layer simulation. Once you are familiar with these tools, the expanding to other layers and systems is actually would be easy. So, let me now go through the exact course content. We have some lectures, so I have characterized them in terms of topics. And so, we will talk about introduction to course. So, today is the first lecture where we introduced the course. In the second lecture, we will talk about, we will give a short introduction to simulation methodology. We will talk about what different kind of simulations are and how these are relevant for communication systems. Second topic is signal systems, and in lecture 2 lecture we will look at how we can represent signals and systems both in via simulation, how we can model them. Then we will talk about random signals because that is very important part of the communication systems. Here we will look at how random factors can be incorporated. So, we will look at random variables and random signals. We will also try to understand how to imitate the system dynamics. So, we will look at some numerical techniques where we will talk about how to do differentiation integration, and then we will see how we can use them to solve differential equation, and a particular example we may take is about Markov chains. We will also talk about Monte Carlo simulation. So, Monte Carlo simulation is actually an interesting way you artificially introduce random noises or random factors in a system, and it somehow simplifies our calculations. So, we will look at how Monte Carlo simulation can actually help. Then we will actually go to implementation. We will look at link level simulation. So, we will talk about in 2 lecture how to simulate a communication channel, and then we will talk about how to simulate a wireless channel. We will talk about some advanced concepts also, for example, for modern modulation, how we can modify these simulation. We will also look at MIMO systems, which is multiple input and multiple output systems. Then we will look at system level simulation where you have multiple links, and we will talk about first mobile ad hoc networks, MANETs, and cellular networks. And then we will also look at how we can simulate the modern systems, for example, millimeter wave and terahertz system using that. So, these are references. Actually, there is not a very good reference which covers all of the concepts. So, my class notes, class slides and the class videos should be sufficient to understand the complete course. You can to understand MATLAB, because I will assume that you know MATLAB for this course. So, I am not going to cover basics of MATLAB. We will look at the MATLAB examples, but we are not going to cover basic of MATLAB. So, you need to understand how to program in MATLAB, how to write loops, how to apply vectors and run codes in MATLAB. So, that is the knowledge I assume from each of you. And for that you can look at MATLAB documentation, and also I also have a book, numerical method using MATLAB, which you can also refer to, or you can refer to any of the MATLAB resource available online, either on website or in book format, right. And there are very nice videos also available for MATLAB. And then there is also one book, Simulation and Communication System, Modeling Methodology and Techniques, which talks little bit a mixture of theory and simulation, which you can also do if you want to look at more complicated systems. So, that is for advanced reading. But as I said, if you just follow the course notes and the videos for this course purpose, it is sufficient, and in the end I think you should be able to simulate any kind of system you want. Let me go through the grading policy again. It is expected that you learn basic of MATLAB, as assignment, quizzes and exam may be dependent on that. We will have assignments in this course that will carry 30% of weightage. So, make sure to do them. We will have attendance. So, when in the online session you may your attendance will be recorded, and that is 20%, and also your class participation will also be looked over. So, if you ask questions and get involved, that also has some marks in the attendance part. There will be quizzes, 1 or 2 quiz which will carry 10%, and then there will be a end semester exam which will carry 40% of the weightage. So, that is what I want to cover today, and in the next class we will start with what is simulation, what are different methodologies, and how we can do simulation for communication system. So, thank you.